Hello great ones, welcome back to another carpenter example. Here we have the combination wrench and we are going to determine the maximum deformation and the distribution of Van Mises stresses under the distributed load and boundary condition shown in our figure. You can get the geometry from the link in the description. Let's go to Ansys Workbench and conduct this 2D finite element analysis. Let's begin by dragging a static structure into our project schematic. Let's double click on engineering data. Let's add a new material by clicking here and give it a name. I'll call it stainless steel. With this still selected, let's go over to our properties and let's double click on isotropic elasticity. And for the Young modulus, let's key in this value 1.93 e to the 11th, and for the Poisson's ratio, let's key in 0.27. Let us close engineering data. This takes us back to our project schematic. Let's click on geometry, and where we have advanced geometry options, the analysis type, change that from 3D to 2D, and make sure you have surface bodies checked. Now let's right click on geometry and import geometry. So let's navigate to where our file is, select it, open, and let's double click on model to open our study. Before we set up our study, let's navigate to our units and make sure you have metric millimeters selected. Let us navigate to our project outline and click on geometry, and where we have 2D behavior, make sure you have plane stress selected. Let's expand the geometry and let's select wrench surface, and let's navigate down to material here and expand that, and let's apply our stainless steel material. Now let's create our mesh. So let's right click on mesh, insert, let's apply a method, and let's select our geometry, come here, apply. Let's right click on mesh once more, insert, sizing, and let's select our geometry, apply. Let's right click on mesh and generate mesh. Let's just right click in our window here, isometric, and let's click on zoom to fit, and here is our mesh. Let's right click here, let's go down to view and go back to a front view. Now let's apply our boundary conditions. So let's right click on static structure, insert, and we'll start by inserting a fixed support. Make sure that you have your edge controls selected, and let's select these edges. So use control and just select all of them and hit apply. Let's right click on static structure again, insert, this time our pressure. Okay, for the definitions where we have defined by, let's change that to a vector, and we would use a downward vector to do that. But before we do that, for the magnitude, we need 2 megapascals. Okay, and let's go to geometry. We need to select our point of pressure, our pressure point, apply. Okay, and for the direction, or vector direction, let's select this edge. Okay, apply. And before we apply, let's change the direction to downward and hit apply. And that's our boundary condition. Now let's retrieve our solution, but let's double check our element size. So go back to mesh, body sizing, and let's make sure this is set to 1.5. Okay, now let's generate our mesh again. So let's click on mesh, let's right click, go back to our isometric view just to confirm. Okay, right click and view, back to our front view. Okay, body sizing, much better. Now let's go down to solutions, right click, insert deformation total, right click on solutions again, insert stress, Van Mises equivalent stress, select that, now solve. With equivalent stress selected, let's review the Van Mises distribution, and we can clearly see at the two entrant corners here. If we go to our isometric view, you can see it here as well, and also the opposite side. Okay, so these two corners here, we can see that we have a magnitude ranging between 159 to, let's say, approximately 160 megapascals, and this is actually below the yield strength of stainless steel, which is 207 megapascals. And if we go back to zoom to fit, and you see this looks quite deformed, but is actually below the yield strength of stainless steel. That is because of our view. If we go to true view, you would see that it's not that deformed. So this is just a scale to analyze our solution. Okay, so let's leave it here for now, and let's analyze total deformation. Let me just zoom out a little bit, and you can see that our maximum deformation occurs at the two endpoints of the left side of our wrench, and it has a magnitude of 0.138 millimeters. So let's now go back to true scale, and this concludes our simulation. Thank you for watching. Bye for now.